Hello. This is the last so-called class we'll have this semester, but I just want you to understand that if we had another week, we would do some of these problems, but the purpose of this presentation is to combine everything you've learned about, or not everything, but some of what you've learned about the design of open channels and how it is related to stormwater drainage, but also look at reviewing some of those equations for you. So for the final exam, what I need you to understand is the basic concepts. Not the equations here, but the concepts, okay? So in case you didn't know, you know how to design a retention pond, and basically is by calculating the volume that we have done, either using the rational method or the SES method or the CN curve method. And all of this information in terms of how to design, what equations to use, and how to build this hydraulic structure you can find in El Paso Drainage Manual and also in the Design Standards for Construction. We'll go over some of those. You have access to both manuals in your Blackboard shell. So if you look at Design Standards for Construction, you will see drainage and drainage structures in section 2. Detention basins are included there, and so it tells you what is the equation that you will use, and here we have 200 acres or less, and if you have more than 200 acres, then you see a different section 2.9, but it's basically what is in the manual. I want you to know that everything we've covered here is not anything that you could not find on your own, but I'm just directing you to those two manuals for your information. And if you go to another city, they'll have similar guidelines for the hydraulic structures. And this is for a city, not the county, but the city. The county does not have something like this, so it would be good engineering practice to follow this same guidelines. So here is the requirements. Whenever you look at how is it built, it will give you information on the slopes and what kind of foundation you need to have, and linings and all of that. So I encourage you to look at that, and that's where you will find specifically what you need to know. Whenever we talk about stormwater collection systems, this is one of the most important components in urban infrastructure. And when we talk about stormwater collection systems, we refer to the stormwater runoff, how you convey that runoff to a nearby stream, river, detention basin, lake, estuary, or ocean. Not for us, of course. So, important concept is that road and highway design should minimize the danger resulting from stormwater runoff. So you don't want a street that's totally flooded, even though we have some streets that are totally flooded, but that is something that needs to be resolved. So what we want is to use the streets as a temporary conveyance of that stormwater flow. And you can see here how you have the depth of the flow that is that you should have, and then it should be ponded to a width T, okay, which is not necessarily all the way to the middle of the road. So these are some concepts that are important to remember. So you have the gutters, which are the channels on the side of the road, and they're designed to convey some of that stormwater to the inlets, and then the spread is the T, how much you can let it spread on the road. So the good news is that gutter sections are like open channels. So you will design those sections as open channel. A word of caution is that now you have two slopes because you have your street, right? And the street itself has a slope, but also now you have a transverse slope as x, which is really important as well. So you have to take that into consideration. So being an open channel, you use the Manning equation, for example, and A is the area of the channel, but if you're in the street, this is, if you look here at the depth of the flow y, this is your y, then you have your t, and then of course now you have, let me use the correct nomenclature, Sx. Okay, so this is the volume, and then your hydraulic radius you calculate using the wetted perimeter, right? So which is in this case these two values. Okay, so important to note that whenever you have a drainage conveyance structure like a street, because streets are designed to be part of that conveyance system, you have to take into consideration what is also the drainage area that will be part of that flow, or will produce a flow that will end up into a stormwater inlet structure. Okay, so we need to take into account, for example, when we look at the, this is green, I want the red. So we have here the drainage divide. So even though you can have drainage from an area that is conveyed into the road, all of this will be conveyed into a stormwater inlet structure. And that flow that goes into the inlet is really important. We have to calculate that peak flow. Now you don't have a lake or a river that will help you delineate your stormwater shed. Now you have to think of what is the area that contributes to that street, and then from that street, what is the peak flow going into the stormwater inlet. As usual, remember you have to calculate the time of concentration. We gave you some equations, and in order to design, you equate the time of concentration to the duration of the storm for your design purposes. This is a review. We can calculate the time of concentration using, for example, the SCS method. This is one of the equations that we looked at, which is a good equation to use whenever you have small watersheds. Okay, so this is your peak flow that needs to be conveyed into a stormwater inlet using the rational method. Okay, from the design storm regulations, you calculate the intensity, and in the El Paso drainage manual you can calculate those intensities depending on which area of town you are. And then this peak flow that you'll calculate in order to design what is the depth, the slope, and what is the T, that is what you will incorporate into the design for that open channel, which is the street. Okay, so here we're combining calculations of peak flow for the drainage area that contributes to the flow into the inlet, and you'll have to design that open channel area in the street to convey that flow. And this is the equation that you would use. Here we have Manning's in this case. So those are the two equations. Remember, you can pause the video. Something important here is this S that you have here. Remember, this is the slope of the open channel, not the transverse slope. Okay? The transverse slope you'll use to then make sure that the water is flowing into the inlet and from the street, and the S into the inlet. Okay? So that's how it's combined. So that area is the area of the open channel. Once you have the area, the regulations and manuals will tell you how to calculate that depth Y and that T. Okay? So these are some of the suggestions that are provided for the spread of the gutters, depending on the design return period that is needed. You know that the construction manual will give you what is the design return period that you need, and this is an example. And as I said, we're not going to go into actual calculations because we don't have the time, but at least you will be prepared to know where to look for this information. Okay? So this is an important difference, right? I wanted to point out that this is the area of the drainage and this is the area of the open channel, although they have the same A for area, it's different areas. Okay? Water is conveyed from the street to a stormwater inlet, and these are some of those inlets. One of the things that I have done in the past with students is to go around and collect photographs of different inlets and identify them by name. We have different inlets here on campus. So you can have a grade, you can have just a curb opening or a combination. And again, that you can have the uniform, the road as part of that volume, but it has to be conveyed into that inlet structure. So when you have inlets with grades, one of the things, and even without grades, is that not all of the flow that goes into that grade will be going into it, or 100% of the flow. So keep in mind that this goes at a certain velocity, so some of it will not go down into the stormwater structure. And it can happen even with open grades, but it tends to happen more whenever you have a graded inlet structure. So whenever we have, especially the grade inlets, this is what we call the inlet efficiency. As I said, you have your flow, and some of it will go over it and not go into the inlet, and usually this happens more with a graded inlet structure. Okay? So remember, you have El Paso Drainage Manual, you have El Paso Design Standards for Construction, and if you are in Texas Department of Transportation roads, then you use the TxDOT manual. Okay, here's the design manual for stormwater plan, and then this is TxDOT. And the great thing about TxDOT is that they have an interactive manual, so you can go to the TxDOT web page and find the section that you're interested. So you have here storm drains, for example, you have culverts, channels, everything, all of the things we've reviewed in this class, you can find here, and they have them, how they specifically apply to TxDOT structures. Okay, so you go to storm drain inlets, and you can find all the information that you need with drawings and designs. Okay. Something really important is to avoid clogging. I mean, an open grate will, an open inlet, I should say, would reduce the clogging. If you have a grate, there's going to be more clogging due to debris and everything that is carried by the runoff. And as I mentioned earlier, I am not presenting this with the purpose of going through the design equations, but I just want you to see examples of design equations that you would use, and this is specifically for text.structures, and then you're required to intercept 100% of the flow. What is important is that you know what is each variable, and depending on the type of inlet structure, you'll have to look at your drawings and see what is what for those. Okay. Where would you locate the inlet? Of course, you're not going to put it in the highest spot of the street. You have to put it in some sort the water collects with no other outlet, along the curb when the gutter capacity is exceeded, and you don't want that water to go into the sidewalk, for example. And it's important to place it in locations where the water has spread into the street and it affects traffic. So you need to put an inlet there. It's important to never have a bridge that accumulates water, especially in areas where you can have ice, so that you don't just have blocks of ice on bridges. So in bridges, this is especially important. Okay. And of course, at intersections where traffic, for safety reasons, but all of us have been driven by intersections where there's accumulation of water, and so that is one of those things that needs to be corrected. Now, so we have looked at stormwaters, at watersheds, and from the watersheds, you calculate that flow that will go into the street, and from the street to the stormwater inlets. And from the stormwater inlets, it has to be conveyed through pipes. And of course, important to obtain the pipe size to convey that peak discharge. So you use the peak discharge to calculate the conveyance structure, which is the street, but now all of that goes into the inlet structure, and from the inlet structure now you have pipes that convey that runoff. Okay, so and this is really important because you have here different blocks like you would in a city, right? And then you have to look at different manholes that are in this location, right? Let me see. I thought I had a drawing with, yeah, I think it's this one. So here you have the stormwater pipe design example, but we're not going to go into that. But what is important is that here you have this first structure, and then you have an inlet here. So this pipe conveys the flow from this sub-watershed, but also whatever comes, from another direction here. And here is the stormwater that has the flow from this area plus this area. So whenever I look at, for example, this inlet here, this inlet conveys the flow from this area and also from this area. So these two areas, and then when I go to this pipe, it conveys all of the flow here, here, and here. So as you can see, the point in this is that whenever you're calculating the pipe sizes for stormwater drainage structures, It's not a one size fits all, because you can have, for example, this pipe here that it's conveying flow from here, from here, from here, from here, from here, from here. So you will need a bigger pipe that goes from manhole 4 to manhole 5. So you have to use your equations to design pipes based on the flows, okay? Let me go back. I apologize. So for design of pipes like this one, you can use manning, for example, and then the area of the pipe is when it's full. So you want to convey all the flow, okay? Now, remember that manning we used in the past, and we could also use manning for open channels. So this is just an example of how to calculate those pipes. You can use other equations, okay? And then the pipes come in standard designs, so in 3-inch intervals from 12 to 24, 6-inch per 25, 24 to 48, and 1-foot intervals thereafter. So whenever you calculate the required diameter of the pipe, well, first the area, then diameter. What you need to make sure is that if you have 11 inches, then you want to go for the higher that you can find on commercially available, 12 inches, okay? So this is another example where you have 1, 2, 3, 4 basins. So whenever you are discharging in the manhole or stormwater, C is from basin 2, but now from basin A is basin 1, but now B is discharging this 2. So the pipe that goes here has to be larger. And then this one conveys all of the flow. So that's very important. So it's not as straightforward, okay? Now, I gave you an example. As I said, I'm not going to go over the math of it. I just want you to understand, for example, if I gave you something like this and I would ask you which pipe would have to be the largest size or which pipe can be the smallest size, that you understand, because you're discharging into a stormwater inlet some subbasin, and as you go downstream in the pipe, you're accumulating all of the stormwater from different subbasins, okay? So that is it for now. I just want to show this, and remember that to calculate the sizes, we can use manning, for example, and then you look at IDF curves or intensity equations like in the El Paso manual. And then one thing that I should mention is the time of concentration. So the time of concentration now has to be the time of concentration for this watershed plus the time it takes. So for example, if let me delete everything here for one moment so that I can be more specific. So let me delete all of this messy slide. Okay, so whenever you have the time of concentration, you have a time of concentration for that subbasin, right? And this is what I will use to calculate this pipe. But now, for this second watershed, I have a time of concentration of 10, but then I have to also include the time it'll take, time of concentration from the manhole to here. So there's two things that you need to add, okay? So time of concentration, you have to calculate for each manhole, and you use the largest of the two. You compare your time of concentration for upstream manholes and the time of concentration for upstream manholes plus pipe flow time, okay? So, and then the runoff coefficients, again, you use the weighted coefficient for each one of those multiple areas. Remember the time of concentration, you have to add all of these components, and this is kind of reviewing your equations. and they are in your textbook, and I would provide you with those, but the El Paso Drainage Manual also tells you how to calculate those.